Hello ladies and gentlemen, good to see you. Today I'm going to be giving you a bit of extra information around why we calculate the sample standard deviation and the population standard deviation in different ways. So you'll remember from last week we covered descriptive statistics, and within that we looked at different metrics for calculating the spread of data or different properties for the underlying distributions of data. And this is very relevant to understand both the phenomenon of interest, but also whether our data conform to particular requirements in order for us to carry out more sophisticated techniques, as we'll get to later within this class, later within this semester. So the standard deviation measures the dispersion of data around the mean. And within the lecture last week, I described how we have a particular way for calculating the sample standard deviation and a particular way for calculating the population standard deviation. So you'll remember that for calculating the sample standard deviation, what we do is we obtain the sum of the squares. So we subtract the mean of the sample, so x bar, from every individual observation that we have. We square them, and then we add all those values up to get the sum of the squares. And then we divide by the number of entities within the sample, so n, and then we subtract 1 to get the number of degrees of freedom, so it's n minus 1. And then we, after averaging all of those values, we essentially then take the square root again so that we return the standard deviation back in the same units as the actual underlying data. The question is, well, why do we do n minus 1 when we calculate this differently for the total population? So if we want to calculate the standard deviation for the total population, then we carry out the same math. It's very similar, except we just use the total number of entities in the population at large. So we do not subtract 1 from this value here. And that's because potentially you can introduce error and bias into your sample standard deviation. And I spoke about this last week, but I thought today I would just work through a little bit of code in R so that you had a more thorough understanding of the way that this is calculated and how this bias is reduced by this one small change in how we calculate this metric. Okay, so let's spin up R. I'll share this R code so it'll be available for you. When you go into this particular R code, bias underscore example.r, then you'll be able to import the data set which we're using. So here that's rivers. So if you aren't familiar with the rivers data set, let's have a look at what's included. So you'll remember that if we type help and enter the dataset name, we'll be able to look at a description of that particular data. So rivers is part of the datasets package, which is inbuilt to R. And basically it contains the lengths of major North American rivers. So that is what these data here correspond to. And the data are collected by the US Geological Survey, USGS. They're provided here in miles, not kilometers, so miles, for 141 major rivers in North America. Okay, and we're able to inspect these. So here we've generated a histogram. You'll remember that we've done this quite a few times now in the different lectures. So a histogram of the lengths of these rivers. So on the x-axis here, this is the length going from 0 up to 4,000 miles. And the binned increment for the histogram is every 500 miles. And then on the y-axis, we have the frequency, so the number of observations within our data set which fall into each one of these categories. So up here, we have the Mississippi River, so at almost 4,000 miles long. We actually have very few entities within these upper value bins, whereas the majority of the observations within our data set are in the bottom 2 categories, essentially. So most of them are below 1,000 miles each. Okay, so that's given us a bit of an understanding as to what the data are. Now what I'd like us to do is to calculate the population standard deviation for the data that we have. So let's do this by hand. And let's remember that we might not always have the population standard deviation available to us. So you'll remember that it's expensive to carry out a census where you survey each individual. And therefore, often within statistics, we will sample populations because it's cheaper. It's more efficient in time. It's cheaper in monetary resources if we're able to obtain a representative number of entities which represent that population, and then we don't have to go out and get data from every single person. For example, we might just be able to sample 10% of people or of businesses, and that might give us enough of an understanding to produce data on the phenomenon of interest. And this is a standard survey statistical technique used by many statistical bureaus, particularly, for example, for economic statistics, where you want to generate information on labour markets or business activities, potentially on a quarterly or half-yearly basis, but at least once a year normally. These statistical entities will produce this type of data. So in this case, we just calculate the population standard deviation so that we compare the production of these other metrics against what the truth value is here. So if we calculate the standard deviation on the population, then we have to take the sum of the squared values and divide by the number of observations within our data set. And that produces the population standard deviation here, which I've assigned to this this variable. And actually, just for the sake of clarity, I've used the round function. So if I didn't use this, it would spit the number out with a lot of additional decimal places, which we don't really need right here. So I was just rounding it off so that we were getting a population standard deviation of about 492 miles. So that's a perfectly acceptable level of precision. Okay, so now we know what the truth value is. Let's take some samples of the individual observations from the river data that we have. So this inbuilt function here in R called sample is a way to take n rows from a table. And that's exactly what we're doing in this instance. So we're saying, can you give me 5 rows from the dataset rivers as a sample and allocate it to this variable named Sam? And when we do so, we end up with the sample of those values placed here into the global environment. Now let's calculate the population standard deviation. So that's using length n, so capital N here. And we're getting a value produced. And now let's produce the sample standard deviation using the sample calculation method. So that's using n-1. And you can see that despite the fact we've only taken a very small number of entities, the second way that we calculate the metrics, so using n-1, actually produces a number that is closer to the true population standard deviation. And that's because when we draw a sample from the total population, we're probably unlikely to get the extreme values, and we're more likely to get values that are within the, some part of the distribution, probably closer to the mean rather than the extremes. And therefore, what we're trying to do here is to take this into account. Otherwise, we will systematically underestimate the standard deviation within the sample. Okay, so one issue that we have here is that we're only choosing 5 observations at a time. And that means that that sample might not be fully representative overall. So if we look at the variability when we draw another 5 rivers, and we calculate these metrics, you can see how much these numbers are jumping around, are changing because we don't necessarily have a representative number of entities. So we are able to select, for example, 50 rivers. So that would be 1/3 of the data approximately. And we're able to re-estimate these metrics. This time we again have quite a large amount of variability. And you'll notice that because of this change in the sample size, you don't always get a value that is closer to the population standard deviation when you calculate the sample standard deviation as we've done here. So remember the true value is 492. Actually, in this case, the way that you calculate this metric using the population approach is actually closer. Then when we rerun it again, actually we get the reverse result. And that's because there's variability in the population size that we've got. So really what we want to do is we want to keep drawing those samples and taking the mean of those sample standard deviation values that we get. And this will reduce out the variability that we're actually obtaining just by taking a single sample from the population. So let's try this now using what's called a loop. So essentially this is a standard computer science technique, and it's also called a for loop because it starts with for. And this is one of the beauties of using computers to calculate these statistics. If you went back 100 years, people would have to calculate this all by hand. Now we're able to use computers to generate, for example, 10,000 individual samples from the data that we have, as we're going to do here. And we're able to do that very quickly, very efficiently. And this is where computers are able to outcompete human activities. So what we want to do is to first create empty vectors for the population and the sample, as we're going to carry out, we're going to use different math equations to calculate those different values. And what we say in the for loop is for I in 10,000, so that's going to change the I number to 1, 2, 3, 4, 5. It's going to count all the way through to 10,000. And each time it does it, it's going to take a sample, so 50 individual rows from the river data. And then it's going to calculate using the population standard deviation approach and the sample standard deviation approach. And it's going to put the values that are produced into these vectors that we have here. And the index just helps to put it into the right place within that vector. So when we run this for loop, so here we've entered the function, we've created the vector, and now we're going to, we've created the vectors and we've run the for loop. So all of the data is now produced here so that there's 10,000 values. And we've produced that metric 10,000 times. And now what we're able to do is to take the mean of the p vector, so the way that we calculated using the population standard deviation, and we're able to calculate, take the mean of the sample standard deviation approach, which is here is 482. And we're able to compare these to what the overall truth value is. So let me just pull this truth value down here. So we know that the actual standard deviation for the population is 492 miles. And when we calculate using the population metric, so that's capital N, what we get is an underestimation of the true standard deviation. And then when we calculate using the sample standard deviation, so that's n-1, we get a value that's actually closer to the population standard deviation. And this, as a consequence, is why we subtract 1 from the total number of entities in the sample in order to get the number of degrees of freedom. So I hope that that's provided a quantitative example of why we we use this particular approach. It helps to reduce the bias within the sample estimation for the sample standard deviation. Okay, so I will share this particular piece of code. It will be on Blackboard for you to download and look at and understand. And please do let me know if there are any other areas of uncertainty which perhaps they weren't explained in full depth in the class, or if there's other areas of interest to you that we haven't covered in the syllabus yet. Do reach out to me. I'll look forward to hearing from you. And I hope you progress well with this, and I'll look forward to seeing you in the next videos for the coming week. Thank you. Goodbye.